As we continue into section 5.3, and again, this is another thing that's kind of presented in a little bit of a different order than I've grown accustomed to in teaching calculus courses in the past. Yeah, we've done, I mean, a lot of calculus courses will introduce antiderivatives slightly, talk about area underneath curves, and then progress into the integrals because, and I'm not going to like go into great detail here. Essentially, when you find the area underneath of a curve, and they're showing what they refer to as Riemann sums here, where basically we use these rectangles to approximate areas underneath the curve, and obviously the less wide we make those rectangles, the more closely it approximates the area underneath that curve. The area underneath that curve represents the antiderivative or the integral. So, that's basically the long and the short of it. So, like for instance here, so they do give you some information about Riemann sums. There's several different types of Riemann sums that you can actually make use of. You have upper and lower bounds, and you have, a trapezoid rule, and there's also a Simpson's rule for Riemann sums. And they don't get into all that in this course. But, the whole idea behind that is to learn those things, and then you kind of go into, okay, well, this is what the result of it is. And basically, the whole idea of it is that the integrals that we come to know are circumstances that as these widths of these rectangles, as the limit of those become closer and closer to zero, um, then that's when we start getting, the true area underneath the curve, and that's what the antiderivative or integral is. So that's kind of the long and short of this here. So when I ask you to approximate the area underneath of a curve, f of x equals x squared from 1 to 2 by 5 rectangles, and to use rectangles with equal bases. So they're kind of breaking it down for you to let you know that, okay, well, each width is going to be, essentially in this case, 0.2 in width. And so when you set up these rectangles, starting at 1, you're going to have one that goes from 1 to 1.2, one from 1.2 to 1.4, one from 1.4 to 1.6, one from 1.6 to 1.8, and one from 1.8 to 2. Other decisions that often have to be made is whether you're going to use the upper value or the lower value, because you can actually draw two rectangles between 1 and 1.2. And in some cases, your textbook does show some that are using the left-hand corner of those rectangles, which means oftentimes it is a lower estimate. Sometimes you're going to have an overestimate because you might use the right-hand corner, and sometimes you use the midpoints of them. As I said, there's different variations of it, and your book really kind of goes into it very minorly, so it's not a major topic that you have to be aware of, but you are asked some questions regarding it. Um, so if we're looking to find these areas, basically, I have the width of each one. I know where the heights are. So essentially, I have each one of these rectangles, and I calculate their area, which is just basically base times height, and I simply add them together and get about 2.04. Therefore, the area underneath the curve is approximately 2.04 square units. Now, I have two that are marked as your turns. I'm actually going to do one for you because, as I said, this particular set of examples that they give you here are not the best in the world, is explaining it in this particular PowerPoint. So I want to kind of walk through, what they're showing you here. So if we want to do, like for this one here, if I want to find the area approximated by those shaded rectangles, I can see in each one of these instances that each one of these widths are 0.5. Okay, so each one of these are going to have a width of 0.5. Now, I can see that these are going to be the estimates of the height of these rectangles. So this one here would be like e negative 1 power. This would be e to the negative 0.5 power, because we are looking at the function y equals e to the x. This would be e to the 0 power, which we of course see as 1. This would be e to the 0.5 power. So that represents the heights of each one of these. So if I wanted to approximate the area for this, I would say essentially I would have e to the negative 1 times 0.5 plus e to the negative 0.5 times 0.5 plus e to the 0, which is just 1, times 0.5 plus e to the 0.5 times 0.5. Sometimes you'll see in calculus books, they'll just say, okay, well, if I just take basically all of those left-hand corners, e to the negative 1 plus e to the negative 0.5 plus e to the 0, which is 1, plus e to the 0.5, and multiply that all by 0.05 or 0.5. Because, I mean, basically it's like the distributive property. That's going to give me the area. And so the area here is about 1.81 when I plug that into my calculator. So that's essentially what they're doing here. Now this one here, I mean, if we would discuss it more, we could see it's an underestimate because I have all these gaps like right here and here underneath the curve. So I mean, the area of these rectangles would be a value that we expect is lower than the actual area between the curve and the x-axis here. In this one here that I'm going to let you work on, this would be an overestimate because I can see that I have blue areas like right here and here that are above, you know, the x-axis, that are above the curve. So I would expect this to be an overestimate of what the true area was. But find the approximate area of these shaded regions using these three rectangles as reference. So these areas, I mean, I could see again, each of the widths is a unit of 1, which makes that easy to work with. I mean, because each you know, when I do base times height, you know, the base is going to be 1. The heights, I have this one as a height, I have this one as a height, and I have this one as a height. So those heights is going to be 1 over the square root of 1, because this is where the x value is for that y value, plus 1 over the square root of 2, plus 1 over the square root of 3. Now technically I'm going to take each of those heights and multiply it by 1 because that's what the base is, but I really didn't have to write that because multiplying by 1 doesn't do anything. So the final answer for this is about 2.28. Again, they don't have you do a whole heck of a lot with Riemann sums. I mean, we are going to talk about area underneath curves, and we're going to look at doing the areas between curves and bounded by curves, but that's what the integral actually does. You know, basically the number of rectangles that, you know, we're able to get, because if I decrease the width of each rectangle, then I get more rectangles that I could fit, you know, between two given values in the curve. So you know, the more rectangles I can get, the closer the approximation is. So basically, you know, this is all the explanation as to basically if I'm looking for you know, if I'm looking to find the area between the x-axis and the curve, that eventually, you know, it is what what we would define as a definite integral. We were doing indefinite integrals before. Indefinite integrals, we would just come up with a formula, you know, which we would also call the antiderivative. For a definite integral, we're going to get an actual value. You know, we're going to be able to evaluate that for a certain amount. So, so you're going to see this notation here, where, you know, I have a lower number and an upper number. We're going to see how we're going to handle that. But essentially, that derivative, or that integral, is the limit as n approaches infinity, where n is the number of rectangles you have underneath of the curve. You know, for each one of these, you know, function values times what they call delta x. Delta x represents the width. So these are actually getting closer and closer to 0 as this goes to infinity. So, you know, as we get closer and closer to that, then the area is approximated by the integral. This is just notation that says how do we evaluate it once, because basically the way we deal with an integral is that, a definite integral is that we evaluate the indefinite integral, and then we use this notation to say, okay, well, once we get our new function, this is the function we get from doing the indefinite integral. And of course, it wants to do that funky extraneous line all of a sudden. I do the definite integral to get that formula, but then I evaluate it for a and b, where I basically put the top number in, I put the bottom number in, and I subtract the two. So, this notation here, if I end up with x squared from 3 to 5, I would put the 5 in first, the 3 in, subtract them. It's not a big, difficult thing to do. So, the fundamental theorem of integral calculus shows how to evaluate definite integrals by using indefinite integrals. So, I mean, basically, we take the indefinite integral, like we've been doing in 5.1 and 5.2, and then we evaluate them for the given circumstance. So, case in point, as we go through this, if I wanted to find the integral from 1 to 2 of x squared dx, the first thing I would do is I would, it's continuous, and I was to keep in mind, if there's any discontinuities, I had to try to account for that and, plan around that. We're not going to worry about that quite yet, so we don't have to go into that right now. So, what I'm going to do is, I know that if I integrate x squared, I get 1/3 x cubed, and I'm now just going to evaluate that at 1 to 2. I don't have to put a plus c in, because basically, if I was looking at this as being essentially, 1/3 x squared plus c going from 1 to 2, well, first of all I do is I plug the numbers in for the x's. So I'm going to have 1/3 2 squared plus c minus 1/3 1 squared plus c. We're assuming it's the same arbitrary constant, so here I'm going to have 4/3 plus c minus 1/3 plus c. The plus c's would just cancel at that point. It's going to be a minus c here because I get distributed. So the arbitrary constants would cancel. I'll get it with 3 over 3 and get 1. So I could kind of ignore the arbitrary constants when I do a definite integral. That plus c basically, and I must have messed that up. Yeah, it was cubed. I think I did squared. Yeah, 1/3. Yeah, so that should be 8, and that should just be 7/3. If you got the right idea. So I may end up with the same answer, but the plus c's don't have to play a role in this because of the fact that, they'll eventually cancel out anyway. Now, all these rules are showing here are basically saying that the same rules we had for indefinite integrals apply to definite integrals. So here's your turn. I want you to take a look at this and evaluate the definite integral of x plus 1 squared over x squared dx from x values going from 1 to 2. Well, much like we had to do when we did the indefinite integrals, because we did one very similar to this, is before I worry about doing any integration, I'm going to simplify the expression I have in there first. So integral from 1 to 2, I'm going to get x squared plus 2x plus 1 over x squared dx. And now I'm going to carry out the divisions. So x squared divided by x squared is 1. 2x divided by x squared is going to be 2 over x. And 1 over x squared is going to be x to the negative 2 power. Now when I integrate these, the integral of 1 dx is just x. 2 over x is like having 2 times 1 over x. And the integral of 1 over x is the natural log of the absolute value of x. So here I'm going to have the natural log, or 2 times the natural log of the absolute value of x. And then this last one, I'm going to add 1 to that, divide by -1. I don't have to put the plus c in because I am going to evaluate this eventually from 1 to 2. The c's would cancel anyway. So I have an expression x plus 2 times the natural log of the absolute value of x minus 1 over x, all this evaluated from 1 to 2. So I plug in the 2 first. Now that I know it's a 2, I can kind of get rid of the absolute value there because it's not a big deal at this point. And now here I'm going to put 1 plus 2 times the natural log of 1. Again, I can just put the parentheses because I know 1's positive at that point. Minus 1 over 1. 2 times the natural log of 1 becomes 0. 1 minus 1. So all of this becomes 0. 2 minus a half is, I could say just 3 halves. Plus, and I could actually go back and say, well, 2 times the natural log of 2 is the same thing as the natural log of 2 squared, so I could say it's plus the natural log of 4. So that's how a very common way they would often produce that answer. If you wrote it as, the final answer as 3 halves plus 2 natural log 2, whether it's parentheses or an absolute value, would accept that, but no plus c. There's no x's involved in this, no arbitrary constant. So basically we now know that the integral is how you can find the area underneath of a curve. Now when we say underneath of a curve, when they say area under, essentially what they mean by that, they use this terminology, but it's not the most accurately described terminology, because when they say area under a curve, this is actually meaning the area between curve and x-axis. It's very deceiving when they say area underneath of a curve, because sometimes it's not really under, because if you're looking at a situation where here's the x-axis and your curve is doing something like this, well, they might want this area here. That's not under the curve, that's over the curve. So when we're talking about the area underneath of a curve, we're talking about the area between a curve and the x-axis. And just so you know, in these kind of instances here, when we start talking about, areas like this, up here I would have a positive area, down here would be a negative area because it's underneath the curve. So, you got to keep that in mind as we end up doing some of these things too, because you can actually get a negative area when you start talking about integrals. So, for an example for this particular problem, we want to find the area underneath under y equals 24 minus 6x squared from -1 to 1. Now, here, using the term under the curve makes sense, because we can see if I go between the curve and the x-axis, I am under the curve. So I want to find that area, so I'm going to do the integral from -1 to 1 of that curve's equation, 24 minus 6x squared dx. So they do the indefinite integral and get 24x minus 6 times 1/3 x cubed, which will become 2x cubed, and I'm going to evaluate that from -1 to 1. So when I plug the numbers in, I get 24 minus 2 minus -24 plus 2, which eventually just becomes 44. So the area is 44 square units. So it's your turn to give it a try. Find the area under the curve. Now again, remember what that means. Between the given values 0 to 8. So when I find the area underneath this curve, going from 0 to 8, all I'm really doing is I'm going to be finding, the area under the curve. And I'm not looking for the total area underneath the curve. I'm looking for a net area. So if I do have positive and negative areas, I want the overall net area. This one here, I believe, excuse me, 8 minus 4 times the cube root of x. Basically, the curve kind of looks like this when I go from 0 to 8. So we are talking about this. So it's all above the x-axis. You may want to have a quick graph of on a calculator to see what it looks like. But I just want to do the integral from 0 to 8 of 8 minus 4 times, I'm going to just change it right down to x to the 1/3 power dx. I'm going to take the indefinite integral, so I'm going to get 8x here minus 4 times, I'm going to get x to the 4/3 up here divided by 4/3. All that evaluated from 0 to 8. Simplifying a little bit, I'm going to get basically 3 times the cubed root of x to the 4th power. And I'm going to be evaluating that from 0 to 8. When I plug the 8 in, I'm going to 8 times 8 minus 3 times the cube root of 8 to the 4th. Minus, well, if I plug the zeros into both of those, I just get 0. It doesn't take that long to realize that. And so when I work that out, I get 16 square units. Total cost, again, if I just like anything else, if I'm looking for a total cost, I'm basically looking to plug certain values in to a cost function. So if I had marginal cost, I would integrate to get the cost function, and then if I'm doing a definite integral, it's going to give me the total between two values. So here they're saying, okay, I have a marginal cost that's given by this function here, where x is the number of units. Find the total cost of producing units 100 to 400. So we just have the integral from 100 to 400 of 75 over the square root of x dx. Of course, we move the 75 to the outside because it's a constant multiple. We turn the x into x to the negative 1/2, so we can use the exponent rule for integrals. I would get 75 times 2 times x to the 1/2 power, because basically x to the 1/2 power is what I get when I add 1 to the exponent. If I divide by 1/2, that's like multiplying by 2. I'm going to evaluate this for values between 100 and 400, so I just plug in the 400. I plug in the 100. I evaluate, and I carry through the subtraction, and I get 1,500. So the cost of producing units 100 to 400 is $1,500. But, it goes under the same thing. If I'm looking for a total accumulation, which basically means, like, if I'm talking about, like, if I'm given a speed, then the total accumulation is going to be the total distance I covered. Like a very famous type of, or widely used problem, I don't know if we call it famous, but a widely used type of problem that often gets used for integration in more of a physics type setting is that they say, okay, you have a car, it's hitting the brakes, and it takes 4 seconds to stop. Knowing what its original speed was, how far did it travel in those, like, how many seconds it took for it to stop? So that's a question that's often gets asked. So like what if I going 60 miles per hour, I hit the brake, slam on the brakes, and it takes me 4 seconds to stop. How far have I actually traveled in those 4 seconds? I mean, that could matter. So whether it's cost, distances, amounts of something, it's all kind of the same premise. So, and they call that total accumulation. So basically, I look for the total accumulation given a certain rate. Then I'm just going to do the definite integral between the two values that they mention. And this just kind of goes into the same thing of what kind of things you can look at: productivity, sales rate, marginal cost. So the area of marginal cost is total cost. The productivity, how many pieces per day or pieces per hour you could finish. Then the area is going to represent the total amount that you got done. The sales rate, if that's what your function is, we'll find the area is going to find how many things were sold. So So in this case here, a technician can test computer chips at a rate of -3t squared plus 18t plus 15 chips per hour for hours between 0 and 6 hours. How many chips can be tested between 10 a.m. and 1 p.m.? Now, since t represents the number of hours after 9 a.m., we're looking for, okay, 10 a.m. is at hour 1 p.m. would be at hour 4. So I'm going to set up an integral of this function that we had, -3t squared minus 18t plus 15 dt. I integrate that using indefinite integral techniques that we learned before. And I'm going to evaluate that at 1 and 4 and subtract them. So when I do that, I get these for a grand total of 117. So basically, between the hours of 10 a.m. and 4 p.m., 117 chips can be tested. Now it's your turn. An automobile dealer estimates the newest model of car will sell at a rate of 30/t cars per month, where t is measured in months and t equals 1 corresponds to the beginning of January. Find the number of cars that will be sold from the beginning of January to the beginning of May. So take a few moments here and see if you can come up with the answer to this question. So I'm gonna say here that, ds, which stands for sales, dt, is 30/t. So, that represents the rate of change in sales per month. I want to figure out so what I'm looking to do here to figure out, okay, what's the number of sales? That's going to be the integral from, now since t equals 1 corresponds with January, and I'm going from January to May, I'm going from months 1 to 5 of 30/t dt. This is going to give me my total number of cars sold. So I'm going to have 30 times the integral from 1 to 5 of dt/t essentially, which we know is the natural log. So I'm going to have 30 times the natural log of t, absolute value of t, evaluated at 1 to 5. So I'm going to have 30 times the natural log of 5 minus the natural log of 1. Now any logarithm of 1 becomes 0, so that just kind of goes away. So I end up with 30 times the natural log of 5, which is approximately equal to 48 cars. So basically, since I do have a rate of that, which does change as the months go by, I'm going to end up, with selling a grand total of 48 cars between the beginning of January and the beginning of May. That is the end of this lesson. If you have any further questions on definite integrals, please feel free to ask about them in class. Until I see you there, have a good day.